differentials. I'm going to tell you what a differential is, and we'll get used to using it over time. If you have a function which is y equals f of x, then the differential of y so is going to be denoted dy, and it's by definition f prime of x dx. So here's the notation. And because y is really equal to f, sometimes we also call it the differential of f. So it's also called the differential of f. Well, that's the notation, and it's the same thing as what happens if you formally just take this dx, act like it's a number, and divide it into dy. So it means the same thing as this statement here. And this is the more or less the Leibniz interpretation of derivatives. Of a derivative as a ratio of these so-called differentials. It's a ratio of what are known as infinitesimals. Now this is a kind of a vague notion, this little bit here being an infinitesimal. It's sort of like an infinitely small quantity. And Leibniz perfected the idea of dealing with these intuitively, and subsequently mathematicians use them all the time. They're way more effective than the notation that Newton used. You might think that notations are a small matter, but they allow you to think much faster sometimes when you have the right names and the right symbols for everything. And in this case, it made a very big difference. Leibniz's notation was adopted on the continent, and Newton dominated in Britain, and as a result, the British fell behind by 100 or 200 years in the development of calculus. It was really a serious matter, so it's really well worth your while to get used to this idea of ratios, and it comes up all over the place, both in this class and also in multivariable calculus. It's used in many contexts. So first of all, just to go a little bit easy, we'll illustrate it by its use in linear approximations, which we've already done. The picture here, which we've drawn a number of times, is that you have some function, and here's a value of the function. It's coming up like that, all right? So here's our function. And we go forward a little increment to a place which is dx further along. The idea of this notation is that dx is going to replace the symbol delta x, which is the change in x. And we won't think too hard about, well, this is a small quantity, this is a small quantity. We're not going to think too hard about what that means. Similarly, if you see how much we've gone up, well, this is kind of low, so it's a small bit here. So this distance here is, previously we called it delta y, but now we're just going to call it dy. Okay, so dx dy replaces delta y. All right, so this is the change in level of the function. And we'll represent it symbolically this way. Very frequently, this just saves a little bit of notation. For the purposes of this, we'll be doing the same things we did with delta x and delta y, but this is the way that Leibniz thought of it, and he would just have drawn it with this. So this distance here is dx, and this distance here is dy.